Hi everyone, so today we're going to be going over how to evaluate inverse trig functions. So the three main inverse trig functions are arcsine, arccosine, and arctangent. There's also arccosecant, arcsecant, and arccotangent, but the important thing to remember about these is that just like their trig functions, they can simply be written as 1 over their respective inverse trig function. But the first thing to understand about each of these trig functions is that they are each bound in certain domains and ranges, just as their regular functions are. So the range of arcsine, or the y values that it can exist, are basically limited to the first and fourth quadrants. So this means that it can be between negative pi over 2 and pi over 2. And an important thing to remember with the arcsine and arccosine functions is that the boundaries are actually included. Arccosine is limited to the first and second quadrants, and like arcsine, the boundaries are included. So the boundaries are 0 to pi. Arctangent is limited to the same quadrants as arcsine, but the important thing to remember about tangent is that the boundaries aren't included. Another good way to memorize the boundaries for each inverse trig function is to look at their graphs, and you can always draw the graphs because it's basically just rotated about the line y equals x. So for arcsine and arccosine, you can see that they're limited both in range and domain, both from -1 to 1, and then for arcsine, it's limited from negative pi over 2 to pi over 2, cosine 0 to pi. And then the important graph, I think, to note is arctan, because usually when you're doing integral problems, especially improper integrals, if you ever see an arctan, you should note that the limit as x approaches infinity is pi over 2, and as it goes to negative infinity, it's negative pi over 2. So one of the most common questions is you're going to have a ratio plugged in, and you have to get out the theta value. So arcsine of rad 3 over 2 equals some number. That's what we're trying to find. So you look at this as sine of some theta is going to give you rad 3 over 2. So just from memorizing the unit circle, we know that for this, theta would have to equal pi over 3 or 2 pi over 3. This is where your boundaries come into importance. So only one of these values is going to work because the other exists outside the boundaries of arcsine, and that would be 2 pi over 3 because that one is in the second quadrant. So the answer to this question is just pi over 3. Here's another pretty common example problem, and I'm just going to show you how to work through this because there's one mistake that people tend to make that you should try to avoid on tests and quizzes. So we see this problem, and the first thing we think is tangent of some theta is going to give you -1, or tangent of some x. So you go to graph this, and you know that it's going to be in the fourth quadrant because tangent only exists in the first and fourth quadrants. And so this is going to be at negative pi over 4, because you know that this is just equal to sine of theta over cosine theta, and for these to both be the same, you would have to have it at pi over 4 so that you would get negative rad 2 over 2 over positive rad 2 over 2, or -1. So you're saying to yourself, okay, here's where the theta is. Now you have to find the value. So as I said before, it's negative pi over 4, but some people also tend to write this as 7 pi over 4. This is wrong because this exists outside of arctan's boundaries. So even though that's technically in the fourth quadrant, what you want to remember with arctan and arcsine is that they exist from negative pi over 2 to pi over 2. So instead of going pi over 2 to negative pi over 2, which would encompass quadrants 2 and 3, you have to remember that they're in quadrants 1 and 4, but you have to go, it's easier to go from negative pi over 2 to pi over 2 so that you know for sure that you're only going to be existing in these two quadrants. And so the reason that 7 pi over 4 is wrong is because that's going all the way around to this quadrant when that lies outside of tangent's boundaries. So you have to remember to do the negative version if you're in the fourth quadrant for arctan and arcsine. So the first thing we want to do when taking the derivative of arcsine of x is get this into terms that are manageable and that we're familiar with. So basically, we're going to apply sine to each side, and so you get sine of y equals x. From here, we're going to take the derivative because we know the derivative of sine, which gives us dy dx times cosine of y is equal to 1. Divide cosine of y over, and you get dy dx equals 1 over cosine of y. What you can do from here is recall one of the most basic trig identities, which is that sine squared y plus cosine squared y equals 1. So you get cosine squared y equals 1 minus sine squared y. Take the principal square root of both sides, and cosine y equals rad 1 minus sine squared y. Applying this original formula, you get that cosine y is just 1 minus x squared from over here when we said sine y equals x. So then you know that dy dx of arc sine of x equals 1 over rad 1 minus x squared. Similarly, you can prove that the derivative of arc cosine of x equals negative 1 over rad 1 minus x squared, and the derivative of arc tan x equals 1 over x squared plus 1. So one really common use of inverse trig functions is you're going to see them appear a lot in improper integrals. So the example I have here is from negative infinity to infinity, 1 over 9 plus x squared, and I've just denoted a to equal negative infinity, b to infinity, and I've rewritten the problem as the limits go to each respective infinity. So once again, you can see that we've pulled out a 9 from each of our integrals, and then you get 1 plus x to the third squared, and you basically do the same u substitution as you did in the other problem, remembering to multiply the 3 out to cancel out with the du. And you're just left with 1/3 1 plus u squared du, again, plus the other one with the other limit. And so you can just then rewrite this as arctan of x over 3 solved from 0 to a plus arctan x over 3 solved from 0 to b. This problem becomes pretty simple because we know that 1, arctan is centered around the origin, and 2, it has finite values as it's approaching each infinity. So to solve this, you're just going to want to bring a 1/3 out in the front, and then you know that arctan of 0 equals 0, minus arctan of negative infinity is going to be negative pi over 2, plus arctan of infinity, once again, pi over 2, minus arctan of 0. So then you're going to get pi over 3, and that's it. Now I'm just going to outline some of the most common errors when using inverse trig functions so that you don't make them. So one of the most common errors is plugging in a theta value instead of a ratio. So you plug in a theta value to regular trigonometric functions, but once again, because it's the inverse, you're plugging in the ratio to get out the theta value. It's not so common to do it on homework, but on a test when you're rushing through it, you just have to be really careful of this. The second mistake is the limit as x approaches infinity of arctan of x. So we've already gone over that it goes to pi over 2, so you just really have to cement that. Most people will mistake it for that arctan is growing exponentially, and they think that it's tending towards infinity. But A, you can just think of the arctan graph, or if you forget it, you can also think of the regular tangent graph, which is bounded once again by pi over 2, or negative pi over 2, and pi over 2. So these vertical asymptotes mean that tangent itself also tends towards these values. So that's one way to remember it. The other thing about arctan is you always have to remember its bounds are not inclusive. So while arcsine and arccosine include their bounds within their ranges, it's different for arctan because once again, it's tending towards pi over 2. As it's approaching infinity, it's never actually going to reach this. The third most common mistake is arctan and arcsine bounds. People will look at the bounds as pi over 2 to negative pi over 2. So we know that each of these actually exist in the first and fourth quadrant, but when you look at the bounds like this, you say, okay, it goes from pi over 2 to negative pi over 2, which means that it would exist in these two quadrants. That's a really common mistake, but it's wrong. So you always have to think back to the graph of each of them, or you can just say to yourself, instead of saying these are the bounds, just say that each exists in quadrant 1 and quadrant 4.